Hello everyone, this is Module 6, Part 1 of Chapter 6, Transforming Data Models into Database Designs. Our objectives for this module is to understand how to transform data models into database designs. Remember we started talking about the three database design phases, so we're going to get into the actual conceptual database design phase. Um, we need to be able to identify what our primary keys are and when we should use surrogate keys from our ER models, as well as understanding and determine what our referential integrity constraints need to be put in place, um, how we would represent our tables how we would represent our tables from our ID dependent ER models in our one-to-one, one-to-many, and many-to-many relationships, as well as how we represent our weak tables, our weak entities as tables from our ER models. We need to be able to represent our supertype, subtype as tables, as well as any recursive relationships, and in our ternary relationships when we have degrees of 3 between our entities. And then the last thing, how we would implement referential integrity actions that require minimum cardinalities. So essentially where we're at now is from chapter 5, where we talked about our entity relationship models, or where we developed those entity relationship models um, um, using our ER designs. We want to be able to take those ER models in our design process and then transform those ER models into database designs. So by definition in the book, a database design is simply a set of database specifications that can actually be implemented in a specific database management system product. Okay, so what we need to understand here is that at this particular point, now we need to start taking in consideration what database management system that we're going to be using, because a database design for SQL Server 2014 may differ from an Oracle database design or a MySQL database design. So we just need to make sure that we take those characteristics in consideration, because there may be some slight variances on how we put together our database design from our ER models. Where we're at in the software development lifecycle here, our systems development lifecycle, we're in the component design phase at this particular point, or systems design. We're going to be going from, again, a logical, because remember our conceptual was where we were at before, our conceptual and logical, to an actual logical and physical database design. So we're going to be discussing just some general rules in how we put together our tables and our database designs. However, again, we have to start thinking about some of those physical elements. Again, those physical elements in our design would go back to the actual database management system that we'll be using, so we can take all of those things again into consideration. So the book breaks down different steps for transforming a data model into a database design. The very first step is to create a table for each entity, and along with creating a table for each entity, we need to make sure that we specify what our primary key is going to be used, and then at that particular point we need to consider if surrogate keys are appropriate or not appropriate. We need to make sure that we specify any alternate keys, which is the same thing as a candidate key possibility. And then we need to make sure that for all of our columns or our attributes, we need to make sure that we determine what the null status is, data types, any default values, constraints. And then finally, the last step in step 1 is, just verify our normalization principles. Okay. Step 2, we kind of will create relationships between our tables, because now since we've created a table for each one of our entity. Now we need to take a closer look at that crow's feet notation that we've had in our ER models and create those relationships by the placement of the foreign keys. Okay, so we need to take a look at what our relationships are and the degree of that relationship, whether if it's a one-to-one strong entity, one-to-many, many. We need to identify relationships that are ID dependent. ID dependent entities would be representations of intersection tables or association patterns, multi-valued attributes, and archetype instance patterns, as we discussed in Chapter 5. And then any relationships that between strong entities and weak entities, but that may not be ID dependent. Okay, and then what those mixed relationships are, and then any subtype or supertype or subtype entities. Okay, and then that's pretty much for step 2. And then the last step in transforming our data models into database designs is we need to make sure that we specify whatever logic that we're going to be using to enforce minimum cardinality. And again, that's in our, when we talk about minimum cardinality, we're talking about either an optional to optional relationship, mandatory to optional, optional to mandatory, or mandatory to mandatory. Okay? So as we go back to step 1, step 1 is we create a table for each entity. So as you look through the book, you need to make sure that you understand that how their graphical representation. So on the left, you see in our figure A, in the book, remember we talked about an entity as being a shadowed rectangle with our identifiers in the top portion of the box, and then the bottom portion is our attributes. And then as you can see in B, you'll see that that is depicted as a table where we will indicate our primary key with a key symbol, and then notice that it's a shadowless rectangle, which would indicate that that would be a table. Okay. Now for our assignments and labs and everything else, we've written everything out what I termed as a standard notation, which you see up at the top there, which it says employee, the employee table with the primary key underlined, and then any foreign keys would be italicized. Anything that's not underlined will be considered non-key attributes or columns within that table, other columns. Okay, so this is just to make sure that we understand what we're looking at. Okay, so again, step 1 is we create a table for each entity in our ER models. We should, as you can see here, everything kind of directly maps over in our table design, where our identifiers typically become our primary keys, and then our attributes become our column values in our table. Okay, so when we start talking about identifiers becoming our primary keys, obviously we want to make sure that that identifier fits the characteristics of an ideal primary key. It needs to be short, numeric, or fixed. If it does not meet that ideal those ideal characteristics, then this is the time that we must consider the use of foreign keys. Surrogate keys. If we use surrogate keys, then we just need to understand that, again, those surrogate keys do not add any value to our tables, meaning it does not add any additional information to our table values. It's just strictly going to be used as the unique identifier of each row in that particular table. Okay. One of the things that you need to take in consideration with surrogate keys is there are some database concepts that take the position for consistency. If one table has a surrogate key, all of the tables in the database should have a surrogate key. But then there's some people that take the position that that policy is maybe too rigid, because sometimes you have some columns that do fit our ideal characteristics of a primary key. Like in our example, like a product SKU, which in chapter 2 that we use is a very good candidate for a primary key. So we would need a surrogate key value. But it's really, the use of surrogate keys is really dependent upon the organization that you're working for and what standards that you have to follow. Again, because as we discussed before, every organization is different. So in one organization where they may require you to use surrogate keys for every table, in other organizations that may not necessarily be the case. Okay, so once we take a look at our identifiers and make sure that those identifiers can qualify as our primary key values. If they are primary key values, then we indicate that as such in our table designs. The next thing would be is to specify what our candidate keys are, or in the same thing as what an alternate key is. So an alternate key is the same thing as a candidate key. And if we go back and remember what a candidate key is, remember a candidate key is a column within the table that can determine or can identify every other column in that particular table. Okay, so how we indicate what candidate keys or alternate keys are in a table is with the notation that you see here in the slide, which is the AKN.M notation, where N is the number of the alternate key and M is the column number in that alternate key. Okay, so here's an example of an indication of two tables that were indicated in our logical table designs, or table designs here, where we're indicating in the employee table first, we're indicating that we've chosen employee number as our primary key, and we've chosen email as an alternate key. So when we take a look at email, we see AK indicating as an alternate key, but the 1.1 means that it is the first alternate key that's in the table, and the one that's after the period means that it just is only one column. Okay, where in contrast, in the customer table we see here, we've chosen the customer number as the primary key, and we have indicated two alternate keys within this table. So the first alternate key would be a combination or a composite alternate key of name and city. And notice our notation there with our AK1 indicating it's the first alternate key, and then you see the .1 and .2 after that. That would indicate the .1 would be the first column and the .2 would be the second column. That indicates that it's a composite alternate key. And then the second alternate key is just, again, it's just email indicated by the AK2. And again, the one after the period just indicates that it consists of just one column. Okay, so again, in step one, we're making a table for each entity. Now we're indicating what our primary key values and our alternate key values are. The next step in step one, remember, was to indicate the null status of our columns. Okay, this indicates whether or not the value of the column can be null or it can be empty. Okay. So if we take a look at our example here for the employee table, obviously as a rule, primary key values cannot be null, right? Because that is the way we uniquely identify each row in this particular table. So that has to be not null all the time. But notice our other values or other column values, you have some that can be not null, and you can have some that are null. Okay. It makes sense that the employee number should not be allowed null again, because if we had a row, if that employee number was null, how would we be able to uniquely identify it, right? But we do have alternate keys that we can use in this particular table, just in case, to be allowed to identify those rows. But as you can see, the alternate key for email is allowed to be null, okay, in this particular situation. So, the question should be, should email allowed to have no values? The answer to that is alternate keys are often used just to ensure uniqueness. So marking email as a possible no alternate key means that email need not to have a value, but it has one. Then the value will be unique and different from all other values of email in the employee table. So, really in terms of when it should be and when it should not be no, is really something that you have to take a closer look at. But a general rule is, in terms of no status, you want to limit the amount of values that are allowed to be no because of the ambiguousness of the those entries in cells. We want to make sure that we are collecting information always because no values can cause problems. The next step in step one is we want to specify what our data types are. Arguably, this is one of the most important steps in our database designs because this is putting constraints that is closest to the data that we're collecting. What we see here is just shows you some of the generic data types that are consistent with all database management systems. And in our example here, we notice in our employee table, we're indicating what those data types would be for each one of our columns. So for our primary key, we've indicated that it's an integer data type. For employee name, character with the 50 character constraint on the employee name. The phone number is a character data type with a 15 limit on the phone number, as well as the email. And then we have dates on a hire date, review date, data types, and again, string values for our employee code limited to 18 characters. Okay, so once we have that, now we're at the stage where we've indicated what we transform our entity into a table. We've indicated what our identifiers have mapped over to our primary key values, and we've determined what our alternate keys are in the table, or candidate keys. And we've also indicated what our no, not no values are, as well as our data types. Okay, so at this particular point, we're well on our way to defining what the structure is of our tables in our database. Okay, the next set of slides just kind of give you a breakdown of data types that are specific to a specific database management system. There are not a lot of commonalities amongst the database management systems. However, there are some slight differences. So again, when we say we're just creating a logical database design, we do have to take in consideration these physical characteristics depending on the database management system that we're using. And as you can see, there are some slight differences depending on what you're using and the data types that you're using and the product that you're using. So these are just kind of a reference of, the different types of data types and what your options are. The next step of part one is we need to determine if any default values will need to be supplied by the database management system. A default value is the value supplied by the database management system when a new row is created. Okay, so in this particular example here, and again, why we use default values is this can help us limit those no values, or put in values that are consistent with every record that we need to do, okay, or every record that we need to collect on that particular instance. So in our example here, if you look at the table down there, so we're looking at default values for the item table, and if you take a closer look at this, everything is interdependent on whatever item prefix is entered into the item prefix column. Okay, the default values for the item number is a surrogate key. If you look at the surrogate key here, that's supplied by the database management system. So that's the default value for that. So that's just going to be automatic. The category column in the item table, there is no default value. So that's something that we are going to have to collect and make sure that we take a look at. Okay. Now, here is where the default values really kick in is if a item prefix, if the category is listed as perishable, then the item prefix will get a default value of P. If imported is put in the category column, then the item prefix is going to be I, and then one off in the category would be O. Otherwise, if it's not perishable, imported, or one off, then in our category, then it's going to be an N in our item prefix. Okay, so whatever we put in we put in our category triggers the database management system to implement these default values in these particular columns. Okay, so what we're saying here is that if the category is imported and our item prefix is I, then shipping/purchasing will be the default value for the approving department. But if it's anything other than I imported in the category, then purchasing will be the default value for the approving department. And then the last example here is if perishable is the category, then the default value here would be purchasing for the approving department, and then the shipping method would then be next day. Okay, but if anything other than perishable is in the category, the shipping method would be ground. Okay, so this is how default values can help, again, populate data or consistent data for every instance that we need to collect based off of another value or something that can be supplied by the database management system. So data constraints. Data constraints is how we limit data values. Make sure that you understand the difference between these data constraints. A domain constraint is a column values that have to have a given set of specific values. So a range constraint means we have column values that must stay within a given range of values. An interrelational constraint would be values that are limited by comparison to values in other columns in the same table, where an interrelational constraint would be limited by comparing values in other columns in other tables. Okay, and this would again take us back to what we know and have talked about in regards to our referential integrity constraints on foreign keys. Okay, so the last step of step one would be to verify normalization, as we talked about. Tables should be normalized based on whatever data model we're using. We need to verify that all tables are either in Boyce Codd normal form or fourth normal form for this particular class. Okay. Remember, Boyce Codd normal form, we just need to make sure that every candidate key in that particular table, or excuse me, every primary key is a candidate key in that particular table. And in fourth normal form, we need to make sure that we eliminate any many-to-many type relationships or any multi-value, multi-column type relationships or situations. Okay, this is the end of part one.